there?
An oscillator.
Just a regular oscillator?
No, a simple harmonic one.
How do you know that's simple harmonic?
Look at the way it moves. That motion is smooth and cyclical. Not only that, but if you track that motion carefully and diligently, you could see it moves like this.
What's all that?
This says that the position of the particle is a portion of its amplitude, known as cosine, dependent on time.
What's that Greek symbol? There, next to time.
That's omega, also known as angular frequency. It is a rate of change of radians per second.
Like angle?
Yeah, in a way. An angle is nothing more than a piece of a circle, a part of a cycle. Angular frequency is how much of a cycle an oscillator does per second.
Oh, I see. But according to that relationship, your oscillator always starts at its maximum displacement from the equilibrium. What if I wanted to start observing it right now?
That's where this comes in.
More Greek?
Unfortunately. This is a phase shift. It determines where the particle is at t is equal to 0. So if our particle starts at the amplitude, it has a phase shift of 0. If it starts at negative amplitude, however, it has a phase shift of pi.
More Greek? Why pi?
A full cycle is 2 pi.
Like a circle?
Exactly. A circle is a cycle, and a cycle is a circle. A full oscillation from amplitude to negative amplitude and back again is 2 pi radians. That makes half of an oscillation pi radians.
So half of that is pi over 2?
Exactly, meaning that the oscillator starts at the equilibrium. Come with me, I have something to show you.
What are all of those? More simple harmonic oscillators?
Correct. Now watch this. Let's call this t is equal to 0. Do you see how they're all shifted?
Oh, that one is shifted half a cycle. So phi is pi?
Correct. And each of the oscillators has a phase shift.
Is that a pattern?
That's right. They're organized in such a way that each sequential oscillator has an increasing phase shift. Not only that, each oscillator is equally spaced along the horizontal axis.
Whoa, what's moving to the right?
No thing.
What do you mean nothing? I can clearly see motion.
Not nothing. It's no thing, as in not a particle. See each of those particles oscillating up and down?
Yes.
Well, none of them actually travel from the left to the right or vice versa, yet there's a distinct motion horizontally.
Then what is it?
It's a pulse, also known as a disturbance. It's a wave.
What's that?
A wave is a propagation through a collection of particles. This collection is known as a medium. Each particle transfers the information of the pulse to the next particle. Each particle, oscillating simply and harmonically, all of them organized at a fixed rate of phi per meter.
Organized?
Yeah, remember how we said those oscillators in motion? Each subsequent oscillator's phase shift varies by the same increment, and all of the oscillators are equidistant horizontally. Because of this, we can describe this whole collection by its rate of change of phi per meter. This is known as an angular wave number, k.
Is this related to angular frequency?
On point. While angular frequency is a description of how much of a cycle a single oscillator goes through per time, angular wave number describes the whole collection of particles. Specifically, it describes how much of a cycle the collection goes through per space.
Time and space? Now my head is spinning. At least K's not Greek.
Fair enough. Since that k value is a constant rate of change, we can use this to determine the phase shift of a particle at any given horizontal position. This allows us to replace that general term phi from the other equation with this new expression, kx.
Okay.
You don't seem convinced. Let's take this particle here. Where is it located horizontally?
At x is equal to 4 meters.
And what is the rate at which phi changes per meter?
Well, each particle is shifted pi over 10 radians from the next, and each is a meter apart. So pi over 10 radians every 1 meter?
Excellent. So if we know this rate of change, and we know that the particle of interest is at x is equal to 4 meters, we can
multiply that k by the position to find the phase shift of that particle. So 4 pi over 10 radians. That seems too simple.
It is simple, but not necessarily easy. With this, we can create a general equation that describes the entire collection of particles, rather than each individual piece. Here it is.
That's not much of a change.
You're not wrong. Each particle is a simple harmonic oscillator through time, and they are arranged simply harmonically through space.
My head's starting to spin again.
Stay with me, stay with me. The equation that describes a simple harmonic oscillator's position as a function of time is this, right?
Yes?
And the rate at which the position changes per time is this.
Rate. You mean acceleration?
Yes, the rate position changes per time is known as velocity, while the rate that changes is acceleration, the rate of change of the rate of change, also known as a second-order differential.
But for this new equation, we have two independent variables, time and space.
Correct. So if we wanted to find the rate of change for each, we're going to have to take a partial derivative.
Partial? Meaning only a piece?
Exactly. We will focus on one independent variable at a time, treating the other one as a constant.
They look the same.
Very, very similar. However, note the independent variable for this one.
Rate of change of position over position?
That's right. How y changes per x is known as slope, while we call the rate at which that changes concavity.
Wait, this rate of change of y per x is dependent on y itself?
That's right. This is simple harmonic motion. As I said before, the collection of particles is arranged simply harmonically through space. This is what I meant. See how both of these equations contain negative y? We can set these two equal to each other with a bit of algebra.
Why would we want to do that?
To create a unified expression to describe the wave as a whole. When we do that, we get this. But this can be simplified even further.
Are we removing the calculus?
Unfortunately not. See this expression here?
Yeah.
Let's take a look at the units. This can be simplified to this.
That's velocity.
Yes, making the final equation this.
What happens when we increase the acceleration of a single particle? Does the wave get faster?
While that makes sense, remember, what is the velocity dependent on? The angular frequency and the angular wave number. Recall that the angular frequency of a simple harmonic oscillator is dependent on the parameters of that oscillator. This is fixed until you physically change the oscillator itself. Well, this ratio of angular frequency to angular wave number is fixed as well, and is determined by specific parameters of the medium.
So if I wanted to change the velocity of this wave, I would have to change the physical properties of this medium?
Precisely.
So changing the acceleration of a single particle will change the collection's concavity?
Exactly. Increasing the acceleration will cause an increase in concavity.
Wouldn't increasing the acceleration also change how long it takes for the particle to oscillate?
Very good. Increasing that acceleration would decrease the period, and thus increase the frequency. The resulting increase in concavity would cause a decrease in wavelength.
Length of a wave. The amount of space?
While period is the amount of time for an oscillation through time, wavelength is the amount of space for an oscillation through space.
So frequency and wavelength have an inverse relationship?
Correct. And the velocity of the wave is the constant between them. The velocity of a wave is equal to the wavelength, lambda, multiplied by frequency.
But the velocity is not dependent on them, right?
Right. The velocity of a wave is constant in a given medium, meaning that if frequency decreases, this causes an increase in wavelength and vice versa.
Oh, so that's a wave.
Exactly.